Good afternoon, sir. The floor is yours, Dr. Naveed, sir. Thank you.
All right, good afternoon, everyone. Welcome back to this session. And as you might know already, this session is we are going to talk about the performance-based design. And the way it will work is that first of all, I will give you a briefing about a little bit about what the performance-based design. I'm sure most of you know already. That's why you are joining this session. And then after that, we will start a discussion session. And I will encourage people to, first of all, put their question in the chat box so we can respond to your questions. And also, if you want to add something or you want to comment, please do in the chat box. And then our team will invite you to unmute your mic and even your video. And then so that we can talk to you and other people can also hear you and interact with you. So this is like a more interactive discussion. That's why we're calling it as a forum. Everyone is invited to contribute their views or their questions. So let me just give you an overview of the performance-based design just to set the scene. All right, so that's there you are. So this session, so performance-based design is actually related to the question, is my structure safe? Sorry. I actually talked about this quite a bit in a series of videos that I also shared on LinkedIn, and maybe our team can share the links with you on the YouTube. The question is, how can we be sure that the structure that we have designed is safe? Can we explicitly say that it's safe? What does it mean to be safe? Safe against what? So how do we define safety? How can we ensure safety? Do the codes provide us enough confidence to be able to tell our clients that the structure that we have designed is going to be safe? Or have we checked the safety by ourselves? Or can we check the safety of existing building that has been designed earlier by somebody else, or for which we may not have full information? So this kind of question about the safety of the structure explicitly, or the performance of the structure, which is safety is a part of that, can be addressed by using this performance-based design. We have seen in the morning 2 slides, one from me, one from Professor Murthy, talking about the importance of nonlinear analysis and the importance of performance-based design. So this is going beyond the traditional elastic design, or where beyond the code factor design or factor design in which we assume certain things to be in a certain way. Here we do it more explicitly, more in detail. We talk about the deformation control. We talked about displacement control. Many things, they are the concept that were presented in the morning session. So that's the main topic. We are trying to answer the question, is my structure safe? Explicitly, reliably, and with confidence. And so this discussion can have 4 parts. One is, why do we need performance-based design? And I already mentioned one reason is that we want to explicitly evaluate the performance and the safety issues, and even beyond that. And what is performance-based design? How does it differ from the code-based design or traditional design? And then how do we carry out the performance-based design? And there are 2 parts to it. One is, how do we do it as a process? And how do we do as a task? Because 2 are different. One is that we talk on a higher scale. How do we convince people to do performance-based design? How do we form the teams? How do we do all of that thing, which is at a higher level? One is at a level of detail. How do we create the nonlinear model? How do we select ground motions? How do we define hinges and things like that? So that is there are the 2 parts to how do we carry out performance-based design, and we can discuss both. And finally, what are the benefits for performance-based design? So very briefly, the motivation of the performance-based design has been that the building codes lack the explicit quantification of safety. They just tell you, please do this one, and hope that structure will be safe. But if we don't do something which is in the code, then does it make the structure automatically unsafe? Or if we do something more than the code, does it improve the performance or the safety, and by how much? The most common example that I normally give is that, let's say the code says that for a ductile design or earthquake resistant design, you have to provide the stirrup spacing to, let's say, 100 millimeter spacing in the column. What happens if you provide 125 or 130 or 150? Does it make the structure automatically unsafe because it doesn't follow the code anymore. But what does it mean? Should we go back and break the column and put the stirrups again? Or can we evaluate the performance or safety with whatever we provide? And that's the difference between PBD and code-based design. It does not automatically say that if you don't follow one rule, then the structure is automatically failed or is not usable or must be discarded. No, it says whatever you have, let's see what is the performance. It also tells us where to put most emphasis because it will identify critical things and then we can focus on those and design and detail them properly rather than putting the emphasis everywhere. Like for example, building codes will tell you provide same stirrup detailing everywhere in all the columns or all the beams. But in performance-based design, you can actually selectively do that. And it basically intends to answer the question of safety explicitly and the decisions that go behind that. Performance-based design is basically, excuse me, based on this concept where we say that the performance is related to how the building will be after an event or after an earthquake or a wind or whichever way or a blast or whichever you're looking at. So operational, that means nothing went wrong. It survived perfectly. People can continue doing the work. Immediate occupancy, that during the event, you may have to go out, but after that you come back and mostly it's fine. And you can occupy the building or structure or whatever you're doing immediately after the event. Life safety is that the structure is damaged, but people inside are safe, but the structure may have to be repaired extensively or may even have to be discarded. And collapse prevention is the structure is going to be definitely not usable after this one. But so these are the different levels that we can evaluate explicitly, and we can evaluate them against the damage or the loss, and we can also evaluate them against the performance. So the hazard and the vulnerability or the performance and the consequences can all be linked together in a systematic manner. So that's what seismic the performance-based design is. The overall process is you identify which project is suitable. Not every project may be suitable. And then we convince the stakeholders that performance-based design should be done because this is something that is not common. So the people may not even agree to do this one because for many reasons. First of all, it costs more to do the design. You need more consultants. Clients have to spend more money to get all these consultants on board. And then you have to select the appropriate guidelines. These are not codes, but these are guidelines developed by different people, different organizations. Like Ron mentioned, one of them, the TBI, that he was a part of the team. Then we set up the performance indicators and criteria. How we're going to evaluate, what kind of risk we will assume, what kind of acceptance criteria do we have. We set those, and there are guidelines to do that. Then we carry out the needed studies. More studies are needed because this is going to be very specific to the building. So we cannot assume the code-based zoning anymore. We cannot assume the code-based response spectrum anymore. We have to develop it for the site, going all the way from the surface, the deep and underground, and get all the information that we need for how the seismic forces will be transferred and what kind of risk do we have, what kind of ground movement, motion we can expect there, and what is the probability and all of that thing. And then we select the right tool. What kind of software are we going to use? Traditional software may not work. You may need special tools or programs that have the capability to do nonlinear analysis, and not only nonlinear analysis, to actually do performance-based design, which is bigger than nonlinear analysis. So that's the overall process. So I will stop here now, and then we will start to answer questions and also get some other views from the people who are joining the forum. So let me just stop here, and then maybe we can unshare the screen, and then we will start the discussion. Okay, I see Jason Regan. Jason, is that you, the one from my class?
Yes, it's me, Dr. Naveed. It's
hi,
good
Jason,
to see you again. Yeah, good.
So
It's been a while.
Yes, very good to see you.
Yeah, and good to see Dr. Ong as well.
Yes. Okay. So you have any questions, Jason?
So far with regards to the PVD, I mean, as even currently I'm here in New Zealand working in a consultancy firm. And normally what we did, I mean, we haven't done any PVD design yet. So that's why I'm a bit of interesting. I made a bit of a reading throughout of it, but somehow no experience in dealing that yet. So my question is, like, as you've said earlier in your presentations, like you need to have at least a composition of PVD team.
Yeah.
So it seems like, is there already a guidelines that you have mentioned where we can specifically run through and goes with it?
Yeah, absolutely. So there are several guidelines. But the most common is the Tall Building Initiative, TBI. There are also guidelines from ASC, and there are also guidelines from CTBUH and many other organizations. So there are several guidelines, and I think maybe Mr. On can share the list later. We have a whole list of guidelines that tell you how to start the process. But most common is the TBI is a good way to start, because they also give you good justification why PVD should be done. But so basically the team involves the design consultant, which is the engineer in record. Then it involves the PVD consultant, which are special consultants who do the performance-based design. And then it involves the peer reviewers. That means the people who will review the PVD carried out by the PVD consultants. And then you also need the site-specific team who will do the evaluation of the hazard, the seismic hazard or the wind hazard on the site. So and geotech team. So there are several more people that get involved. And because it's a special type of work, so very high quality or highly qualified teams need to be engaged for that. In fact, AIT and MKA, Ron Klemenzik team, we have worked together on many projects. They review some of our projects and vice versa. So that's the formation of the team.
It's good to know. So hopefully we'll be able to access those guidelines as well.
Yes, sure, absolutely. We'll share that with you. So,
yeah, thanks for that.
Right, thank you. So any other question in the chat? There is one question here. What is the difference between PVD and normal design? As I already mentioned, so normal design, basically we follow the guidelines given in the course, and typically it is Ashim, can you share the screen of the speaker?
Sir.
Yeah.
My question is, see, you mean to say, I am Manjunath, I am a chartered structural engineer, I straight.
Okay.
I worked in Gulf for 16 years now. Presently, I'm in India. I'm working in DLF as vice president. So my question is, so we are we are doing the design using codes, using certain factors, using certain defined principles. So when we design by PBD, that means performance-based design, are we not following these factors?
Okay. Yeah, I think that's a good question. Let me clarify this one. So basically, the short answer is no, we are not following those factors, because those factors are the ones that create all of the ambiguity in the design. So typically, we follow the first principles, and that means we follow the theory of structures properly, and we do a nonlinear modeling. That means we try to capture the realistic behavior of the structure. We not only input the size of the members, but we also input the reinforcement provided, or that is going to be provided the site inside, and then evaluate that, include in the analysis not only the stiffness, we also include the ductility, we include the nonlinearity, we include the energy, all the things that Professor Murthy mentioned in the morning. So all of those things are part of the analysis process. So the code factors, like especially the R factor or these response reduction factors, they are removed. They're not used. The load factors, normally they're also not used except in certain cases. So generally speaking, we do not use those code factors, and we basically remove the factor of safety concept from the design and calculate the real factor of safety available against the earthquake and against the structure. So we let the structure and the hazard fight together and see who wins in a real fight, not with arbitrary factors. Yes.
That's great, sir. Very interesting. Thank you very much.
Okay, all right. So the
Can I
second
add
question is
one
how
more
much,
thing, sir?
how much PVD is economical compared to traditional design? And Munesh is asking this question. So Mr. Munesh, can you switch on the camera if you can? So let me. This is a very good question, and this is something that is asked many times. Which one is more economical? And there is no straight answer to this this question, because because of three reasons. The reason number one is, what are you comparing it against? If the traditional design has been done very well by somebody who has already done a good job and has economized and optimized in many ways and then used the judgment and made a very good design, that is one type of design. Another one is the traditional design has not been done properly. It's not even safe. It's not even satisfying some of the criteria. So we have to make sure that we compare a design which has already been done properly, satisfying the code requirements, traditional code requirements. Then when you come to comparison, then it is quite possible that the hazard levels in that particular site are more severe than what the code assumed or less severe than the code assumed. It is also possible that the structural system is such that it has more redundancy than what the code assumes. So generally speaking, it's hard to say right away which will be more economical. But if done properly, if done right, performance-based design will turn out to be having better performance and most often lower cost also. So basically what we're looking at is a high benefit to cost ratio. So high performance with lower cost. That is the combination that you should get if both the things are done properly. But in some cases, performance-based design may require additional reinforcement or additional things which may not have been considered. But if you use it properly, we can also reduce in some locations. So for example, the most common case is the ductility requirements in the codes ask you to follow the ductility rules everywhere. But by performance-based design, you can find out that in some places which are members which are not participating in the lateral load, then you may be able to not follow those guidelines and reduce the reinforcement over there. Can I invite you to say something about that?
Yes, sir. Yes. So in PVD, what we can say is we are using the materials effectively. We add the materials where required, and we reduce or remove those construction materials if not required in certain structural components. So this is what we can say is a more cost effective design.
Great. Thank you all. So the next question that I can see is which is similar. What is the advantage of PVD over which cannot be achieved by traditional design? You want to do that, On?
Yes, I will answer, sir.
Okay, go ahead.
So let me explain briefly about code-based traditional design. In code-based traditional seismic design, we design only for one level of earthquake in the elastic domain. So we design in old codes like UBC 97, we design for a 475-year return period earthquake only. And we assume that if very strong events come, the building will not collapse. And if a frequent earthquake or service level earthquake comes, the building will be serviceable. But we design only for one earthquake level, a 475-year earthquake, and we follow the code provisions detailing rules. But in PVD, we check the performance explicitly for the strong earthquakes and also the frequent earthquakes. So we can ensure that our performance will be according to the code specified objective, like a building will not collapse under extreme events called maximum considered earthquake, which has about 2,500 year return period. So we will have more certainty in performance. Another advantage is if we want to use the structural system such as innovative systems that are not defined in the code, or some structural systems which are limited by the code due to the seismic zone and height limits. If we want to use those kind of system, we can prove using the performance-based approach that this structural system is working well under the high seismic zones. So these are the benefits we can achieve when we use performance-based approach.
Yeah, like in the morning, you remember Ron was mentioning that they use this shear wall, which is actually not covered by the code method. So they use performance-based design. They also use these BRBs there, And sometimes people now use flat slab in tall buildings, which traditionally the traditional building code will not allow. But by PBD, you can prove that they can still be used. So that those are some of the advantages that you can achieve. The next question I can see is, can PBD be used along with BIM? And how it's going to affect the modern design approach. I think BIM and PBD are two different ways, different things in a way, but also related. BIM is basically, it's giving you the building information in a digital format, so you can maintain all of the information from design to detailing to construction and even post-construction in a simple model. The advantage would be that you can bring the BIM model back into the analysis and then do the performance-based design without having to input many of the provided reinforcement manually. So if a BIM model has been has been created properly, it will be very useful to actually bring it back and use that actual information in performance evaluation. And if it has been updated after construction, then it will be really good. So I think BIM and PBD can work well together if the model has been created and maintained in that way.
Sir, can I add one more thing, sir?
Sure.
Regarding BIM.
Yeah.
These days, in PBD, we are not using BIM too much, but in future, next step, resilience-based design, BIM will be essential in our design process, because we need to handle more data, not only the structural components information. We need to consider the other information, non-structural component information, such as mechanical components, architectural components, piping components in the building system. So we need to if we need to handle that information, BIM will be essential tool in our design process.
Yeah, thank you. I absolutely, you're absolutely right. The next question is, kindly share your experience on approving authority. Now, this is a good question on the approving authority, because generally speaking, the approving authority should agree to allow performance-based design for a certain building. But if you read the codes carefully, the codes already permit a detailed studies or detailed investigation or detailed analysis which prove explicitly the performance of the buildings. And that is part of the code preamble. So basically, PBD is code conforming if you really follow the code's intent, because the code allows you to use systems or things not explicitly mentioned in the code if they can be proved explicitly that they are valid. And performance-based design actually does that. And because there is a peer review, then the quality and the correctness of the performance-based is kind of assured. But in any case, the authorities may still disallow in some cases, but we have not heard a lot of authorities not accepting it. But it's something that we need to be aware of and make sure that authorities in that region are convinced that PBD can be accepted as an alternative design.
Sir, can I ask one more question?
Yeah.
Sir, is there any way to integrate the performance-based design and traditional code-based design?
Yes, absolutely. Actually, at the moment, the traditional design needs to be done first, or sometimes is done first, and then we follow with the performance-based design as a check on the traditional design. So that is one way to do that. That if you do the traditional design, then after that you do, and you get the output, you get the reinforcement, you get the details, and then you can do a performance-based design on that traditional design to verify the performance and make the changes. That is one way. Another way is that we completely do not use traditional design and use performance-based design for the entire process, like one at a service level and one at a collapse level, a safety collapse level. And then we don't do the intermediate design level, because that's not real, that's artificial. The real structure is subjected to two levels. One is frequent service level, where it should not crack, it should be safe, it should be serviceable. And one is collapse prevention, that it should not collapse. And life safety, that should be safe for life. There is nothing in between. And the code is somewhere in between. That's why it's not necessary, but we can do both. The next question is effective stiffness. Am, you want to take that?
Next question is
Adhikari. No. Let me take the one from Ashish about PBD can be
on
used
the software.
Yes, yes, yes. No, no, no. Before that, I think the bridges and all, things are coming very fast. Can the PBD be also applied to the structures like bridges? Yeah, yeah, absolutely. The PBD can be applied for bridges as well, because basically it's a nonlinear analysis for evaluating the performance. So for bridges also it is used, and it can be applied to any structure. But generally we use it for buildings these days. But absolutely any structure can be used. Next question is from Adika. Adi, many of the codes require us to use effective stiffness of members in linear analysis. What about nonlinear analysis pushover? Can you take that?
Yes, sir.
Many of the codes require us. Can you read that?
Yes, yes, I can read, sir.
Okay.
We still need the effective stiffness members that we normally use in linear analysis, because especially in the reinforced concrete members, even we model, especially when we model the nonlinear hinges, lump plasticity hinges in the beams without nonlinear fiber sections. In that case, we still need to consider the effective stiffness modifiers. We normally consider the secant stiffness of the load deformation curve of the member to determine the effective stiffness. But if you use the fiber sections like shear walls, if we consider the in-plane flexure behavior of the shear wall by the nonlinear fibers, in that case, you do not need to consider the cracking stiffness modifiers. The cracking effect will be automatically considered during the analysis.
Yeah. So that's basically depends on how you model things, and ultimately we should get rid of these factors. And if you model it correctly and you are able to model by fibers and by proper hinges everywhere, then it shouldn't be needed, because the stiffness can be read from the load deformation curve that we provide for the member right from the beginning to the end. But because of the simplicity, we can for the initial starting stiffness, we still need to use them. But after that, the stiffness will come from the hinge properties.
So there is one question that we skipped. How much PBD which we done by software is close to practical behavior of real building? Is there any lag in current software which is in development stage?
Okay, so the thing is that because it's a performance-based design is a nonlinear analysis, so we do a lot of, not only who in AIT, but many universities, many people have done extensive comparison of the testing of the structures, physical testing of the structure against nonlinear modeling and analysis, and mostly the results are pretty close. So that means, but it all depends how well you model, because it will depend on your representation of the member's nonlinearity as best as you can. As far as the hazard is concerned, the real earthquake, of course, we do not know until it strikes. But as far as the time history is concerned, for a particular ground motion, if it has been determined properly, then we should get a reliable result. And because there's so much variation in ground motion, that's why the codes require you to not use one ground motion, but use 11 or 20 or even 30 ground motions. And then you use an average of that, because there's some uncertainty in the earthquakes. That's why one single scenario is not enough. Several scenarios have to be studied to make sure that we capture all kind of variations, and then we take the minimum or the maximum or the average, as the case may be. So I think we have to move faster. The questions are coming at a very fast rate. Okay.
The next question, I will transfer to Shabir. What is your recommendation for efficient nonlinear modeling of columns? Do you prefer distributed modeling using fiber model or concentrated plastic hinges? Shabir, can you answer that?
Yes, Mr. Rao. So with regards to the modeling, many people prefer columns with the lump plasticity model, the PMM hinges. You can also use fibers. There are benefits and drawbacks to both of them. So with the fiber, you get the benefit of not having to model your backbone relationship. So you save time on that. You let the fiber define your behavior. But one drawback again is that you don't have any control over your backbone. So if you use fiber, you have to basically take care that there is a point up to which your results are reliable. You cannot expect the fiber to be 100% correct, and you need to know your limits, and you need to know up to what point the fiber model will give you, and after that the results may or may not be reliable. With regards to the lump plasticity model, the good part about that one is that it gives you control over backbone relationships. The one thing that you might have trouble if you want to model lump plasticity models in columns is that if you see ASE chip recommendations, the input that you need to give to get the backbone, actually you don't have that input. You don't have the axial load demands, and you don't have the shear demands. So there are certain assumptions that you might need to make. You might want to go for a conservative backbone relationship, and then put that in your column, and then assuming that you have a certain amount of axial demand and a certain amount of so there are drawbacks and benefits to both approaches. You can opt either one of them, they might work. The important part is just to remember that there are certain limitations of whatever you are doing. If you just know limitations to that thing, you should be good.
Thank you, sir. We will have to move fast, a little bit faster.
Okay,
Questions
second
are
part
coming in.
of this question, I will handle it. Second part is I have seen some consultant not following the target design spectrum, damped less than 5% to be consistent with the structural damping of less than 5%. Okay, let me explain about the damping that we consider in the model. If we use the linear analysis for reinforced concrete building, we normally consider 5% damping for the code-based seismic design. The damping that we consider is the damping coming from the components that we do not consider in our analysis model. So if we carry out the nonlinear time history analysis, we consider the lesser amount of damping because we consider the damping generated from the yielding of structural components in our analysis model. So normally we consider about 2.4% of modal damping in the analysis model. But there are some other damping that we cannot model. Sorry, we consider 2.4% of modal damping in our analysis model to consider the damping that we are not including in our analysis model, such as damage of the non-structural components and also damping from the soil. So those effects are taken into account in that 2.4% of damping. The remaining part, it will be considered automatically during the analysis while the structural members are yielding. That's why we consider lesser amount of damping when we conduct the nonlinear time history analysis.
So we lost track now. Can you check the next question?
Next question is there a limitation of PVD to use for certain importance level building? Yes, we can. There is no limitation in PVD. Actually, for importance building, we better to use PVD. In also PVD guidelines for the tall buildings, they also have the importance factor. If for the importance building, we have to multiply with those importance factor in our responses. Okay, next question is, can we replace normal analysis and design with PVD analysis directly to minimize the cost and time impact in a project? Yeah. As Dr. Naveed mentioned before, there are two approaches. One is we start the initial design with the code-based approach and get the reinforcement information and check with the nonlinear approach and adjust the design. This is one approach. Another one is just design the reinforcement directly for the service level and wind, and then we check directly to the nonlinear evaluation. There are two approaches. But important thing is the building authorities. Some building authorities, they still need to conform the code requirements as minimum. So in that case, you still need to check based on the code-based approach first, and then you modify the design with a nonlinear evaluation.
Okay, most of the PVD analysis are fixed-based boundary conditions and subject to SLE, MC, earthquake. Will there be much difference if we include? So let me take that SSI on.
Yes, sir.
From Jimmy Dominguez. So yeah, so I think we have done a lot of, many people have done it, and we have also looked into this area of including the soil into the modeling, soil structure interaction into the modeling. So there are several effects because of that. First of all is that the soil modeling can change the dynamic response of the building because of the soil stiffness, and this the structure overall stiffness may be changed, and because of the boundary condition, the structure may have larger displacement or rotations at the base, and so that is one effect of the stiffness when we do that. Another effect of the soil structure interaction, which is a deeper one, is how the ground motion is actually transmitted from the bedrock to the structure, and that's a different type of soil structure interaction, in which you do not assume that the ground motion is coming at the base of the structure, but rather the ground motion is a point at the bedrock, and you model the entire soil above that, and you see how the ground motion reaches the structure, and then that's another level of of the soil structure interaction. So if you look at the guideline, there are several ways that you can include. Simple spring is one minimum level that you replace the soil by a simple spring. Another one is nonlinear springs, and also include the damping. Another one is that you use a full solid modeling of the soil, including all of the transmission of ground motion through it, the layers and all. So it can go up to very detailed or very simple. The final impact may depend on the structure type also. I would say for very tall buildings, the ground modeling of soil is not going to change the behavior significantly, the global behavior. It might change the local behavior or the accelerations at some places. So it all depends. There's no simple answer, but generally speaking, if possible, soil interaction should be included.
Okay, next question is, what are different computer software that use in PBD? These days, we are using ETABS and Perform 3D for the nonlinear analysis part in PBD. And another question is, what kind of structures, conventional building or tall buildings, it is more suitable and more economical? That one, actually PBD can be used not only for the tall building, low-rise building, mid-rise building, any type of structures. Not only for the new building, also the evaluation of the existing buildings. Generally, as I can say, it is cost-effective.
Yeah, especially for existing buildings, I think it would be much better to use PBD, because then you don't need to force the entire building to follow the code, because it will not be possible. So by PBD, you can selectively strengthen some portion, like was presented by Professor Penning in the morning. And also we have done a lot of such studies, and we find that the cost of retrofit can be reduced significantly if you use the performance-based approach in that.
Okay, next question is, some international codes mention two different stiffness modifiers for one factor and another for n factor loads. Yeah, stiffness modifiers varies in the code, and also depending upon the practice of the consultants. Yes, stiffness modifiers will vary, not vary, but upon the loading as well. If we if we analyze the ultimate level loads, we will use lesser stiffness modifiers. For the service level load, day-to-day loads, we use larger stiffness modifiers. This is general.
Or maybe people may be misunderstanding. You mean the stiffness will be reduced less and more, because factors will be opposite. So,
yes, I'm sorry.
Maybe you clarify that.
Yes. Okay, for the larger loading demand, okay, we have the cracking will be more, so the stiffness modifier should be the lesser value. Let's say, okay, for example, for the beams, we use ultimate loads of 0.35 for the beams, and for service level, we may use around 0.7 moment of inertia stiffness modifier.
Yeah. So in general, we should not reduce the stiffness too much for smaller loads, and we should reduce larger reduction for higher load, for the factored load. That's what we are saying. Okay. All right. Next one.
Okay, what is the effect in the lateral response overall stiffness of the building when not modeling the gravity columns? Okay, it depends on it is about the load part. Okay, normally when we design the buildings, we have to designate the load part. So generally, the structural components which are not participating in the lateral resisting system, we should not consider in our analysis model for the lateral loads. So, for example, gravity columns or gravity frames, if we have in the lateral system, if we have in the model, we normally release the moments in those members, so it will not, they will not attract the forces from the lateral loads. So you can, so normally we have to ignore the lateral stiffness of those gravity members, but we have to design those gravity members not only for the gravity loads, also we have to detail those members, although they are not resisting the forces, but they have to carry the gravity loads under the large displacements caused by the lateral loads. So we have to provide according to the detailing rules from the code. And not only that, they have to design the second order effects from the lateral loads. For example, not only the moment from the gravity loads, also if that gravity column is displaced, let's say 20 millimeter or 30 millimeter lateral displacement, we have to consider that displacement multiply with the gravity load, the second order moment in the design.
May I just invite Professor Murthy is also joining this session. Maybe he can add some, if he would like to make some comments about what the discussion. Professor Murthy, if you can, if you are here.
Yeah. Thank you so much. It's very enlightening to see the answers that you provided so far. What it seems is that the genesis of performance-based design can better be won by the fact that today design codes are saying that this is the lateral force. So the focus is on the y-axis. And what I want to say is that actually the earthquake is moving the base at the base of the structure. So actually earthquake is imposing displacement. And performance-based design, the richness of that is actually to see how much is the displacement demand imposed and whether the structure has that deformability or not. So that's the strength of performance-based design. And I'm hoping that by learning nonlinear analysis, they will understand the importance of displacement loading as against wind, which is a force loading. This distinction has to come in the classrooms. And I'm hoping that once that comes, performance-based design will not look like something like a monster or something which is magical, but it will become more realistic that we are actually doing displacement loading properly rather than traditional design, we're applying a force and doing the design. In the traditional design, we are unable to answer many questions like what is response reduction factor? If you don't tell them that it's a reduction factor only if you have ductility, then that concept is again coming from deformation loading, displacement loading. This performance-based design is able to address all of them very smoothly. In traditional design, that hiccup is still there.
Yes, absolutely. Yeah, you're so right. Actually, we have found many times that the actual response reduction factor may be just 2, where the code is saying it should be 6 or 4.
Yes.
And
yes.
it is also very interesting to note that the low seismic zone area actually have a smaller reduction factor than larger, because there is the demand of the earthquake is so small, it doesn't cause any yielding, so there's no reduction. So the structure is basically elastic for a low seismic zone, and people are still dividing it by a large factor, bringing it, low below the wind, which is not the case. So I think these kind of things are very important. Yeah, thank you. So thanks so much, Professor Murthy, for really clarifying very, very nicely this whole idea of PVD. So Professor Murthy will also be joining us in the afternoon in the forum. So let's if you have some more questions, we can still continue to discuss. There is any other question?
Yes, sir. Okay, next question is, since performance levels are based on the definition of plastic hinges, can PVD be used if the fiber elements are used and converted their deformations into rotations? Yes, we can use the fiber elements and convert it into rotations, but we have to take care fiber elements can overestimate the deformation. And the next question is, how can we prove that the assumed 5% or 2.4% damping is correct? It is recommended by the code or lab test. The damping in the tall buildings are coming from the empirical test results of the real buildings. So this is based on the test results.
Yeah, let me just add to that, because these days it is quite one of the hot subject is to actually do a few measurements on the buildings, and damping is one of them that is being measured, and also the acceleration. So there's so many sensors that are not installed. So I think it's not possible to measure the damping factors, as well as many other factors that we assume in the course, and verify them. So I think these numbers are getting improved, regularly. Yeah. Next one.
Next question is, since we have conducted the detailing as per the normal code, is PBD has a huge difference when it comes to detailing as compared to the normal code detailing? How much percentage it will differ? Yeah, it depends on the members and also the structural system. For example, in PBD, we can relax a lot of confinement, especially in the shear walls. So if you have the shear wall building, a bearing wall system, you will have a lot of reduction in the confinement.
Yes, and also you can also find sometimes that some members may need. You can also see that the advantage of greater confinement beyond the core detailing. So some location you might be finding that the rotation demand is very high, or something, that you can increase the confinement and improve the response. So those kind of things can be done both ways. Even for columns, we can find the same thing. So I think detailing from PBD is more directly connected to response rather than just rules that apply arbitrarily everywhere. That's the main difference. And you can see the effect of detailing. I mean, if you do a real PBD, you should be able to see the difference between a 5-inch spacing of stirrups and a 10-inch spacing of stirrups in a wall. So I think that should reflect in the analysis that that level of detail is possible.
Next question is, how conservative is PBD as compared to code-based codal design? I don't want to say conservative. It is more accurate than code-based design.
Actually, for code, yeah. So for building a code-based design, you don't really know what the real capacity and real demand is. So conservative or non-conservative is difficult to assume. But I can tell you from the studies that have been done, code-based design, especially for resilience, it may not be good, because even though it may satisfy the safety to some extent, but it may not be able to determine the non-structural damages and other things, which also have a large cost component for the life of the building. So I think there are many studies on that. So that we should always think that the building is more than just the structure. It also has partition walls, it has ceiling, and all those things. They also need to be checked, and they can be protected by a proper PVD.
Sir, next question is for you, sir. For a structural engineer who wants to learn PVD without taking formal graduate study, what is the best route? What references could you recommend?
Yeah, which one is that?
Second last question.
The second last question. The structural engineer who wants to learn PVD without taking formal graduate studies. Yeah, I think it is not about the graduate studies or non-graduate study. To me, self-study these days is quite possible, and that's why we have offered this PMTB, the Professional Masters in Tall Building, which is not a standard or typical graduate study, but it's still a master's degree, but it focuses on tall building and also focusing on PVD. But like I said, you can take courses just in PVD alone, but I can tell you it's not easy. I mean, it takes an engineer with master's degree and all the knowledge, 2 to 3 years of real involved practice before they become proficient in doing this one. So if you're really committed, you can learn. There's so many resources available. So I don't want to relate competence with master's degree or PhD. It's nothing to do with that. If you're good, you understand things, you can learn, why not? So the tools are available, the references are available. If you have the interest, a degree doesn't matter. It's the skill and the knowledge that will matter, and the attitude, like Professor Murthy mentioned. If you have all three, degree is not important.
Okay, the last question is, instead of outrightly following the stiffness modification factors as prescribed? Is it possible to analyze the structure with all pertinent loadings, then check the actual stress demand and comparing it with the tensile fracture stresses of members? When it exceeded, then apply the modification factor. Yes,
Let me take that. Let me
you
take
can
that.
do, but it will be as an iteration process.
You're going, yeah, right. This is something that I always like to talk about. In my opinion, the code cracking factors are really badly designed, unfortunately, because they assume that all members will crack the same way everywhere and for every load case and load combination. In reality, that's not going to be the case. So I think they are a good start, but when we have the better tools, we should be doing a better job. And like Ong said, it should be iterative. The software should be doing code load-based analysis and then modifying the cracking factors as needed and go to the nonlinear when it exceeds the linear properties. And I think we will get there soon, where the software should be able to do multiple analysis for the same building with different loads, with different factors, and then put the things back together. I think there's something that we should be working towards. This whole business of arbitrary, stiffness modifier is a good thing, but it's not really correct. It's not realistic. But this is the best we have at this time, unless we model everything nonlinear.
So one last question, sir. Can we see possibility of PBD acting as common harmonized seismic code? I mean, design a structure and just check performance point analysis for other codes.